Nice to see you. So last time we discussed the introduction of electric current, and we will define what is actually electric current, or we in general define it. So it's a flux of charged particles, whatever it is, in some direction. So it's directional transfer. That's the key moment here. And so that's definition like qualitative. What about quantitative definition? How we determine it? The magnitude of electric current.
This moment charges pass through a certain area in time.
Per unit time. So it's like the rate, how fast charges are. Electric charge is passing through, for instance, cross section of the conductor per unit time. So now, going further, we also introduced such a concept as electrical resistance. Obviously, there is some force which drives charges, let's say electrons in metals. These mobile chargers can move because of internal electric field, which is created in this conductor, and that's why we don't consider this conductor anymore as conductor under electrostatic equilibrium, because we know from previous discussions that under electrostatic equilibrium we do not have any electric field inside the conductor. However, if we trade, then there is electric force which drives electrons in certain direction, but they definitely meet some drawbacks on their way. They interact with the crystalline structure. They dissipate this gain energy, which they gain by electric field doing work on moving them. And there will be some equilibrium conditions and the steady state conditions. There will be some equilibrium directed velocity, and this will be drift velocity. So that defines, together with concentration of charge carriers available in the conductor to be moved, the magnitude of electric current. So we derive this equation where we had density of electric current. J means ampere per square centimeter is equal to magnitude of charge, electric charge of these particles, Q times N, which is concentration of charge particles per unit volume, times Vd, which is the drift velocity of these charged particles because of existence of internal electric field. So we also introduced some integral parameter of resistance of material, which is called actually electrical resistance, R. So who will recall how we define this electrical resistance? Let's say we have some segment of a conductor with given length area. So how we determine electrical resistance of this segment from one cross section to another?
Quantitatively or qualitatively?
I mean, we can describe the equation. There's a simple equation which gives us the relationship between this parameter, geometric parameters, and some feature of the material, the conductor, which actually all put together in certain equation will give us the electrical resistance of this segment of a conductor. So proportional to what? This is length of the segment. Okay. So what's next?
And inversely proportional to specific conductivity and
Area and specific conductivity. So what can you tell about specific conductivity?
every material has its own.
So it's specific. It comes from the name of this parameter. Specific conductivity means that It is unique for each material, and it's kind of normalized per unit volume of the material. And that's why if we take different metals, some other conductors, they will possess different specific conductivity. Obviously, we want high specific conductivity in order to uh, possess, like use this material as a electrical conductor. So let us write down this equation once more for electrical resistance. As you mentioned, it is proportional to the length, reversely proportional to this electrical conductivity sigma, and area of this cross section of the conductor. So we can introduce one more parameter, which is rho, which is 1 over sigma, and that is specific electrical resistance. So quite often you can see that electrical resistance is defined as rho times L divided by A. So that is quite common form to represent electrical resistance in terms of properties of the material and geometrical shape of the conductor. So that is quite straightforward when we have either like cylindrical form or some other defined form of the electrical conductor. However, what if we need to determine electrical resistance of a bit more specific case? So let us consider one example before we move further with our discussion. So let us try to calculate the electrical resistance of a hollow cylinder. That is our internal empty part of the cylinder. So here we have some radius A. Here we have radius B. And what we want to do here, we want to determine electrical resistance between these two surfaces, the internal surface of the cylinder and external surface of the cylinder, means that electric current will flow radially from the center to the external surface. So what we can do, we can define here, if we look now at the cross section, so let us draw here some just cross section of this hollow cylinder. We can define here any radius r, so it will be a circle defined by this radius, and then we can write the expression for small resistance dr as rho, specific electrical resistance, times dr, like small change of this radius r. And here in the, so that will correspond to this small part of the length of the structure. And then in the denominator, we need to have area. So what will be the area? It will be 2 pi times r times L, the length of the segment. So let us define it here. That's the end here. And here we have the length of this conductor. So now if we want to determine the total resistance of this structure, we need to integrate from internal radius, which is A, to external radius, which is B. So total electrical resistance will be equal from integral from A to B. Here is rho times dr over 2 pi r L. And we assume that the properties of the material does not change. So this raw specific electrical resistance is a constant. It doesn't depend on position. So we can factor it out, the integral with 2 pi times L. Here is integral from A to B. And here is dr over R. And that ends up with rho over 2 pi L times natural logarithm of B over A. So that's one of the possible cases when we don't have just standard scenario, when it's really easy to define the electrical resistance. Yes?
So in formula GR is equal to rho GR. Why we divide to L? Like in the previous formula, L was like we.
Well, that's not so. Let me write it here. It's not just L. We also multiply it by circumference of this circle, 2 pi times R. So together, that is area. So cross section in radial direction, like from center to. So that is area if we consider this internal radius, then that's the area of the side area of this internal cylinder. Understand now? So we pick up some random radius, then we consider very small change of this radius dr. And if we extend this circle inside the conductor, it will create side area, which is given by this equation. So it will be 2 pi r, which is the circumference of this circle, times length of the cylinder. So we satisfy this condition. We have length here, which is in the radial direction, and that is our dr, and area in the denominator. So this area is always perpendicular to the direction of electric current flow. Okay, now we proceed further and consider some microscopic model of electrical conductivity. So, as I said before, let us again go through it so everyone understands it. If we have some mobile electric charges inside a conductor, they don't exist in vacuum. They are inside the crystalline structure of the conductor. So this crystalline structure definitely has some impact on their behavior and how they can move inside this conductor. So we exert some electric force on these charges. They start to move and automatically they interact with the crystalline lattice. Depends on the crystalline lattice, they may interact stronger or weaker, and that will define their so-called effective mass. So let's say we know the mass of a free electron in vacuum. So anyone can recall what is the mass of electron?
9.1 plus 10.9
31 kilos. So that is the mass of electron, but inside a conductor, because of interaction of this electron with the crystalline lattice, it behaves with differently. So in order to describe it in a classical way, we need to introduce so-called effective mass. So effective mass, that's kind of how would be this electron moving if we consider it not in the material, inside the material, but somewhere in vacuum. But in order to adjust for the effect of crystalline lattice, we need to change its mass to a different value. And in that case, it will be accelerating in vacuum in the same way as it's accelerated inside the conductor. So that's why, in order to take into account the effect of crystalline structure on mobility of charges inside this conductor, we need to introduce effective mass. So now let us consider an electric charge. We don't specify which kind of charge, it's just general approach inside a conductor. So we have some electric force exerted on this charge. So it's Q times E, magnitude of electric field vector. Then second law of motion, what does it tell us? M. So it will be M, but we put here this star, which tells us that that's effective mass of this charge carrier inside the conductor. And of course, as you understand, it will be a unique feature of the material and temperature and conditions, specific conditions, when this current is flowing through the conductor. So that's effective mass of the charge carrier times acceleration of this charge carrier because of electric force exerted on it. So assuming that we have uniform electric field inside the conductor, we should have also uniform acceleration. So now recall what is kinematic equation for final velocity in the case of uniform acceleration, like motion along a straight line with uniform acceleration. V final is equal to, yes, exactly. So we have all this in vector form, and this is some time t. Or we can go further and write that V initial vector plus Q E vector over M effective mass times time interval t. So now we need to consider this initial velocity. So let us assume that at t equals 0, there is no electric field inside the conductor. What would you suggest this V initial vector average would be equal to? So what happens with particles? Let's see if we can consider kinetic theory of cases which you discussed last semester. What happens with these particles under thermal equilibrium at some given temperature? So they are randomly moving in all directions. And that is thermal motion. So there is some thermal speed of these molecules depending on their mass and temperature. There is some distribution of molecules. But here, at this point, we want to consider also kinematic model of charge carriers. It's also like mobile particles inside the conductor. So they can be, with some level of approximation, considered within this kinematic theory of cases. So they are moving randomly in all directions. So if we consider average vector of initial velocity, when we don't have any electric field, that will be equal to 0, because randomly oriented vectors, when we sum them, they will give us 0. So in this case, for V final average, we can write that it will be equal to Vd vector, and this is drift velocity vector. That's what we discussed last time. That's directional motion, like velocity, directional velocity of directional motion of charge carriers because of effect of electric field. So in the direction of electric field, if these are positively charged particles, or in the opposite direction, if these are negatively charged particles. And then this will be equal to some, like the magnitude of electric charge, electric field vector divided by effective mass, and here we have some T naught. So this T naught is a specific time interval, quite short time interval, between two successive collisions. So what we assume that the charge carriers are accelerated in the direction of electric field during this time between two successive collisions with crystalline lattice. So when they are in kind of free flight, they are experiencing the external electric force. This electric force accelerates them. They gain velocity until next collision. So when they collide with the crystalline lattice, they kind of dissipate this energy which they gain in vibrations of crystalline structure. So that's why we consider this specific interval of interval of time t naught, which is also called as time of free flight of charge carrier between two collisions with successive collisions with crystalline lattice. So now when we have the expression for drift velocity, so far we just introduced it, but now we have a quantitative expression for this. We can come back to the expression for current density, J, and that is concentration of charge carriers times their charge of each of these particles. And we also have Vd, which is the magnitude of drift velocity. So now we can substitute here the expression. So it will be n times q r squared times magnitude of electric field divided by effective mass of charge carrier in the conductor. And here is this interval, like time of free flight, t naught. And with some rearrangement, we can write here n, concentration of charge carriers, q squared times t naught divided by m star, which is effective mass, and here we have electric field. So this will stand for what? Do you recall Ohm's law in differential form? We introduced last time. J is equal to sigma specific electrical conductivity times E. So that is Ohm's law in differential form, and that means we can write here sigma is times E. So for sigma, for specific electrical conductivity, which we previously just introduced as parameter of a conductor, we have an equation now. So that is concentration of charge carriers, q squared t naught over m star. Yes, sigma, specific electrical conductivity. We can also write for specific electrical resistance. So that is 1 over sigma, and that will be m star over nq squared t naught. So look close to this equation. That's important, and that really shows you how specific electrical conductivity is defined by properties of the material. So concentration of charge carriers, that is a unique property of materials. It tells us how many. So we assume at given temperature, because all of these parameters may change with temperature, of course, but for given temperature, concentration of available free charge carriers is a unique feature of the material. Then this T naught, time of free flight, that will define how, roughly speaking, densely this crystalline structure centers, which like atoms of the material are packed, how easily charge carriers can move around them. And obviously that is also related to effective mass, how much this crystalline structure suppresses the motion of charge carriers inside this material. So obviously, if we increase temperature, then these parameters may change. For some materials like metals, concentration of charge carriers is assumed to be temperature independent, so it's so-called degenerated case when we don't see any increase of charge carrier concentration because we already have so many of these free electrons in metals that their behavior on temperature is negligible dependence. And however, these two parameters, they will change because with increase of temperature, this vibration of crystalline lattice will increase, and the conditions of interaction between charge carrier with the crystalline lattice will change. So obviously that will have some impact on the parameters T naught and effective mass. Is free flight, time of free flight of charge carriers. Huh? Depends what's the question, but if you need to find one unknown, the others should be given, sure. But probably there will be a question to find time of free flight when other parameters are given. So
that I'm using only this one, not this.
mm,
Or
what do you mean this formula? If you have in the problem sigma and concentration of charge carriers and effective mass, then you use this formula to determine unknown.
the time and the given parameters.
No. You will be given all parameters which are necessary. So don't worry about that. Don't need to invent anything.
Ways to find time without these parameters. Oh no.
Well, sure, you can go for advanced solid state physics, and then you will be able to determine this parameter, but that's not going to be part of this course. Don't worry. So now we proceed further once we already clarified all key features of the electrical properties of the material, let's say, and how they are related to geometric features of the conductors. Eventually, we get this electrical resistance as an integrated parameter for a conductor as a part of electrical circuit. Now let us talk about electric power. So obviously we have to deal with it because we have some electrical generators or batteries which provide some electric power to the circuit, and we have conductors with certain resistance where this power is dissipated. So under steady state conditions, this input power from batteries and dissipated power on resistance should be equal to each other. So let us consider a very simple electric circuit. So that will be plus minus terminals of a battery. And here we have a resistor. We neglect with resistance of these wires. So we have just resistor R with electrical resistance R. And this electric generator battery which generates potential difference delta V at its terminals. So let us consider points A and B. And here will be points C and D. So what happens with electric charge when it moves through points A and B in this direction? There is some work done on electric charges inside the conductor, and this work will be equal to like change of its potential energy will be equal to Q, the magnitude of electric charge, times change of the potential between these 2 points, like potential difference. And that is delta V, the potential difference at the terminals of the battery. So we let these charges to move along the electric circuit, and then when charges are moving through the electrical resistor between the points C and D, this gain energy, which they obtain from the battery, will be dissipated in this resistor. Why? You can consider it from this point of view of microscopic nature of electrical conductivity. Charge carriers need to move through this resistor and this like conductor, and they will interact with the crystalline structure of the material of this conductor. They will start to push left and right the atoms in the crystalline structure. They start to vibrate. So that's the mechanism how you transfer electrical energy from this battery into just heat dissipated in this conductor. So under steady state conditions, we have equal input and output. So that should be the increase of potential energy of electric charges at the battery should be equal to dissipation of energy on this conductor. So now we can write what will be the rate of dissipation of energy at this resistor. So we can write that d du over dt, it's like first derivative over time, will be equal to dq times d, we can use delta v over dt. So that will be dq over dt times delta v, because delta v, the potential difference, is a constant parameter. And what is this? This derivative, first derivative of electric charge over time, it's electric current I. So it's the rate how fast this charge is transporting through the conductor. So that will be electric current I times potential difference V. So current times potential difference will be equal to the rate of energy dissipation. In other words, it will be, so what's the rate of energy dissipation? That's power, which is dissipating on the resistor. So we can write that power, P, that's energy per unit time. That will be I times delta V. And assuming that delta V is equal to I times R, we have shown this previously last lecture, so product of electric current and electrical resistance, we can write that dissipated electric power in the form of joule length heat on this resistor will be given by I squared times R, or delta V squared over R. So that's most common form of this dual length heat, which dissipates on a conductor with resistance R and current which flows through this conductor equals to I. And if we consider units for current as ampere, then we consider units for potential difference in volts, and units for this power will be in watt. Watt, like 1 watt. It's 1 joule per 1 second. So let us talk about this moment here. P is proportional to I squared. As you see from this equation, we have this proportionality, and let us assume that we have some constant resistor which we cannot change. So we cannot make it smaller. And we want to make sure that we have minimum possible energy loss over this resistor. So what would you recommend to do looking at this equation? We need to decrease the current because it's not just proportional, it's in second power, so it's kind of the dominant parameter here. And any suggestions how we can transfer the same amount of electrical energy while we decreasing current? We need to increase voltage. So that is the instrument, let's say, which allows us to do that. Since we operate our electric grid in like it's AC and alternating current electric grid, so we will discuss it obviously later in details. But the key message here that when we have fixed resistance, and it's important because we cannot get our resistance of these electric lines from generating power station to consumers, they cannot be, the resistance of these wires cannot be equal to 0. So we can make them as small as possible, but still they will be unfortunately quite significant. So in order to reduce losses, that's what happens at electrical generator. We have voltage around, like depends, but around 10 kilovolts. But then we need to increase, like so use the step up transformer in order to increase voltage to well, even up to 1 million volts, megavolts. Then at such high voltage currents will be relatively small. We will lose not much of electric power by transporting through long distances. But then obviously you don't want to provide such a voltage in apartments. That will not be a good solution. So you need to step it down. So there are sequence of transforming systems which allow to step it down first to 10 kilovolts and then redistribute at a local grid, and then at close already to consumers, they are stepped down to 220 volts between the phase and 0, or 380 volts between two phases, which are delivered directly to the consumers. So that is quite a complicated system. Obviously, it would be better to transport in without any changing the voltage. However, this is a fundamental reason why this has to be done. because electric power dissipating over a resistor will be proportional to electric current in second power. So now let us summarize our discussion for today. We introduced, we continue to discuss the electrical resistance, and after introducing specific electrical conductivity or specific electrical resistance as a parameter of semiconductor, or sorry, the conductor, we considered the microstructure of conductors and considered this microscopical nature of electrical resistance, which shows us that we have some mobile charges. They experience electric force exerted on them. In the meantime, between two collisions during this time interval called time of free flight, they are accelerated with constant acceleration if electric field is constant. And then we can determine the drift velocity. Once we know drift expression for drift velocity, we can use concentration of charge carriers, charge magnitude of the charge, and this expression for drift velocity in order to determine expression for specific electrical conductivity. So it includes time of flight, effective mass of charge carriers, which is defined by mass of the charge, real mass of the charge carrier in vacuum, and interaction between this charge carrier with the crystal lattice, and also obviously concentration of charge carriers, which also is a parameter of the semiconductor or conductor material. So we also discussed the electric power. So if we have this simple electric circuit where we have battery and conductor, charges gain some potential energy while they are moving through battery, and when they are moving through the conductor, because of this interaction between charges and the crystalline structure of the conductor, they dissipate this energy. Under steady state conditions, they have equal rate gaining potential energy and dissipate this energy at the resistor. And we have shown that electric power, which is dissipating over a conductor, will be equal to the product of I squared and R, which is resistance of this conductor. So that is important equation, this expression for Joule length heat dissipating on a conductor through which electric current is flowing. So that definitely you should remember. Okay, thank you very much for attention for today. Have a good weekend and see you next time on Monday.